Now, if we didn't think about the Earth, if we thought about the Earth is stationary, the Earth doesn't move at all, then momentum seems to not be conserved. So physicists came up with a way around that. They talk about an open system and a closed system. In an open system, I can have objects that are influencing what's happening that are outside the viewing area, in a sense. In this case right here, if we concentrated on the marker, that would be an open system because the Earth was influencing it. Or I could treat it as a closed system and I bring the Earth and the marker both into it, look at both of them, and I see that the marker falls and the Earth comes up a little bit. So they typically say momentum is conserved in a closed system. It is conserved, it's not conserved in an open system, but it is conserved if we expanded our system to make it closed. Now, I'm going to guess what you're thinking right now. You're saying this is great, but where are the numbers? Let's do some math. Okay, we'll do that. Questions before we actually do some plug and chug? Do you want to point out, as you'll notice in the notation, momentum is a vector, which means in unison. That'd be cool. What does it mean that momentum is a vector?
Goes in a direction.
Yes, direction matters. So just a quick side note here, the momentum and impulse, that deals with, that's a vector quantity, which has, the nice part is you don't lose direction when you start working at this. Energy, on the other hand, is a scalar, so you lose direction when you deal with energy, but it has the convenience of you're not dealing with direction, so it's a little bit easier mathematically. You just have to interpret it slightly differently. So more complete, more difficult, less complete, less difficult. All right, so I have, let's go back to object or box or whatever you want. I'm going to say the mass of A is 3 kilograms and the initial velocity is 4 meters per second. So we'll just start out with, initially, what is the momentum of box A? That is the velocity. Say it again? Yes. How do you get that?
Mass
Yeah.
times speed.
You're multiplying. All right, so we've got 2 points here. One, I originally did not intend this, but I wrote it down. What is, I established something when I set up the problem. What did I establish and where did I actually do it?
The direction.
What about the direction?
We already have one box going to the right.
Okay, so, establish that direction. What is that direction? Besides to the right.
Positive.
And at what point did I say that was a positive direction?
Kind of did.
Wait, say it again, Caleb?
You didn't really just say it, but kind of gave it to us because that was positive, I guess.
Where did I give it to you that it was positive? Yes. The fact that the velocity is positive here indicates that it's going in the positive direction. Normally, I just write the speed is 4 meters per second, and then you can establish what the positive direction is, but let's just go ahead and make it explicit. All right. So this is a positive. Writing it's optional. But units, what are the units here?
From the box.
The units of the momentum of the box.
Meters
meters per second. So we had momentum, this was mass times velocity, which is 3 kilograms times positive 4 meters per second.
Kilogram meters per second.
It is as simple as kilogram meters per second. There is not a nice simplified one word version of it. Now, in one of the videos I talk about if you want to create your own unit, you can, there's some limitations on that, but watch the video for that. So the initial momentum, positive 12 kilogram meters per second. You could, if you wish, well, let's think back over here. I said that this was equal to that, this is equal to the change in momentum for A. They have to have the same, that has to have the same units as this, so otherwise there's no way they could be equal. So if this is kilogram meters per second, this is also, but what is the SI unit of force?
Newt. Kilogram meter per second square.
Okay, otherwise known as,
Newt.
yeah, Newton, and SI unit for time.
Second.
So a Newton second is the same thing as this. These are equal to each other. They're both equally valid. I've had some students make up their own unit, given the restrictions, and some students use this and some students use that. So. Oh, by the way, I made a reference to the word impulse before. I will not give you my most obscure clue. But this right here, force times time, which is the same as the change in momentum, this is known as impulse. And the obscure clue to have people try to guess what it's called is when someone suddenly buys you flowers, that is called impulse. Perfume ad from the 70s. I'm sure all of you remember it. I think in the commentary, I give a link to the YouTube video of the old ad. All right, any questions about how we got 12 kilogram meters per second? So we'll make the mass of B 5 kilograms, and it's going to the left at 2 meters per second. So the initial speed is 2 meters per second. What is the momentum of, this is of A. This is the initial momentum of B.
Meters per second? -10.
Oh, -10.
Yes. The velocity is negative, that is a crucial thing. So -10 kilogram meters per second. Seda, was that a look of, I can't read this handwriting, or a look of, how did you get that? Okay. Questions? All right, let's up the game. Now, in textbooks, I don't think Hewitt does it, but in most textbooks, they differentiate between a capital P and a lowercase p. It's sort of a 99% rule. Lowercase p typically is the momentum for an individual object. Uppercase P is the momentum for several objects. It's very difficult in my handwriting to know what's capital and what's lowercase unless it's next to something. So this is supposed to be a capital P, those are lowercase p's. I'm not real picky about that thing, but. What is the total initial momentum?
2 kilograms meters per second.
Did Caleb, you said it? What'd you say?
2 kilograms meters per second.
Yep. you get that?
12 minus 2.
Just add. Nothing complicated there. It's a one-dimensional problem. Technically, you're adding vectors. You have a vector that's 12 to the right, and then plus a vector 10 to the left, and your resultant is 2 to the right. But that's the total momentum initially. They are going to collide. The system only has these two objects. There's nothing else that's influencing it. It is a closed system. So these two objects are going to collide. What is the total final momentum? As we just mouthed, the same.
-2 meters per second.
This is conservation momentum. Well, I got the total beforehand. They're going to collide. As long as I don't have anything else interfering with them, it's got to be the same. Momentum can only be transferred from one to the other. It can't go somewhere else. So if they stick together, how fast will they be going after the collision? All right, so I know that the total momentum after the collision is 2 kg/s. And that's got to be equal to the total momentum afterwards. If they collide, if they're now stuck together, first off, if they stick together in the collision, this is known as a perfectly inelastic collision. And again, there's a video where I talk about the naming perfectly inelastic collision, which I often abbreviate as just PIC. Inelastic means they're going to lose energy. Perfectly means that it loses the most that it can lose, which happens when they stick together. So what's the mass after the collision if they stick together? What is the mass after the collision?
2 kilograms.
You said 2 kilograms? No.
Zero.
You said 0? Somebody said 0? Not 0. I got a 3 kilogram mass and a 5 kilogram mass that collide.
Is it negative 64?
8 kilograms?
Yeah.
No, the total.
The total after?
Yeah, because the velocity is 4 and negative 2.
Oh, no, they don't.
They don't.
It doesn't. The total momentum afterwards is positive 2. How'd you get 64?
Because of the m velocity right beside it 2.
Yeah, I've got the units of kilogram meters per second. So you're multiplying the 8 kilograms and
8 times 6.
were you doing 8 times 6?
No, it's like 8 times 8.
How'd you get the second 8? Oh, 4 times 2?
Yeah.
Oh, yeah, no, it does not work that way at all. So afterward, this is 8 kilograms. Because they're stuck together, it's now one big blob times the final velocity. So the math problem we're dealing with is 2 is equal to 8v. That's the math problem. We're solving for v. So the final velocity is, depends on if you're a fraction fan or a decimal fan, 0.25 units.
Meter per second.
So in which direction will these two objects move after the collision?
Right. Right.
Yes. Because as we were working this, we did not, the direction was already taken into account. we got a positive answer for our final velocity, and so therefore it's moving in the positive direction, which is to the right. We did not lose that information during the problem. All right, questions? We're about to do another exciting one. Oh, yes, Ileana.
How did you get 8 again?
This is, so perfectly inelastic collision, they're gonna stick together. So after the collision, they're now stuck together, it's now one object. This is 3 kilograms, that's 5 kilograms,
Oh,
so that's how it became 8.
okay.
Other questions? All right, let's see, I'm gonna keep that initial condition, we're just gonna change what happens afterwards. That's still, all that stays the same. So now what we're gonna do, they're not gonna stick together. So this is before. And then after. A is bouncing back this way at 1 meter per second. What is the final velocity of B? We now have the power to do that. If we were using Newton's laws to solve this, if we were using F equals ma, we would have to know when they hit, they apply a certain force, they will apply more and more force, and then it will become less and less. If you actually, we have the stuff to do it, but if you looked at the forces that they exert on each other as they hit and then bounce off, the magnitude of the force, that really doesn't work on that. The magnitude of the force, basically, they're not touching, then they touch, it's gonna be roughly looking something like that. The force is not constant. It has some maximum force. So they collide, they hit some peak force, and then they separate. It's much more difficult because you don't have a constant force, you don't have constant acceleration. So now, this is an inelastic equation, potentially, I guess we don't know yet. Whether it's inelastic or not depends upon, well, we'll get a final answer. It does require knowing about kinetic energy before we can do that, so it's just not perfect. All right, total momentum beforehand is still 2 kilogram meters per second. That does not change. After the collision, still 2 kilogram meters per second. It's still a closed system. I have only these 2 objects. Nothing else is influencing it. What is the momentum of A after the collision? Momentum of A after the collision. Again, mass times velocity.
Three.
You got 3? Who said 3? Okay, 3 what?
Meter per second. Meter per second, yeah.
You lost a unit.
The kilograms.
Yeah, kilogram meters per second. All right. And one other thing you missed. So close. Direction.
Negative.
Negative, yes. So afterwards, this is negative 3 kilogram meters per second. I know my total is 2, A has negative 3, So what is the total momentum of B after the collision? In other words, what can I add to -3 so I get 2?
Five plus five.
The math problem we're working with there is 2 is equal to -3 plus some unknown. That's the math problem we're working with. Add 3 to both sides, get 5. So the total momentum of the B has to be 5 so that we get a total of 2 for the whole thing. Yes,
How'd you get -3 again?
she told me.
I know.
Jennifer, how'd you get -3?
Mass times the velocity.
And this was for object A, the mass is still 3 kilograms, that didn't change, and it's going 1 meters per second, 1 meter per second to the
Okay, I
left.
didn't see that.
It's a perfectly decent scrawl, you should be able to decipher my scribbles.
Very nice.
All right, we still haven't answered what the final velocity of B is. I know it's positive, a positive number here, 5 kilogram meters per second, and that's gonna be equal to the mass of B times the final velocity of B. What's the mass of B? So what is the final velocity of B? See if someone else will get the same answer. Here's the math problem we're working. I have my final momentum is equal to mass times velocity. That's the math problem we're working.
1.
1 what?
Meter per second.
Say it again.
Meter per second.
And it is positive. Which says that it actually is moving to the right.